Yeah, hello. This lecture is on the chapter on probability, and so as you can see here, the contents will be on talk about sample space and events, probability of an event, equally likely outcomes with conditional probability and dependence, and so on. So we'll cover this material in a series of lectures. So when you talk about probabilities, what does it mean to say the probability of something? Start with some terminology, and the very first thing to think about when you talk about probabilities, start thinking about probabilities. It's probability is a model to measure uncertainty or randomness in things. So first thing we're going to look at is a random experiment. You can see here the random experiment. So start with that notion of random experiment, which means anything that involves obtaining observations. Tossing a coin, throwing a die, polling to see whether people prefer candidate A or B for some office, or whether they like Pepsi or Coke. Inspecting an assembly line to see whether items are defective or not, counting arrivals at emergency room. So all of these are examples of where you can obtain observations, and they represent random experiments because the outcome is not always certain. We don't know how many arrivals at an emergency room will take place at any given hour. Okay, so that's now random experiment. That's what it is. That's where you start. Now we have another concept is the population. Population is we've seen this in data analysis, so it has a similar meaning here. It's the set of all possible observations. So basically, if you repeat the experiment indefinitely, all these possible observations you can observe would be the population. Like if you toss a coin repeatedly, you're going to get heads and tails. So that's your population, heads and tails. If you throw a die repeatedly, you're going to get either a 1, a 2, or 3, or 4, or 5, or 6. So you'd get this is your population, and so on. Outcome of an experiment. So you perform the experiment. We're talking here about the random experiment. And what's the outcome of an experiment? And there's an elementary outcome or simple event, which is one possible outcome of an experiment. Simple example, if you throw a die and you observe a 6, that's a simple event. Now an event or a compound event is one or more possible outcomes of a random experiment. How is that different from elementary event? Well, basically, if you throw a die and you are interested in observing an even value, so that's 2, 4, and 6, so that's a compound event, right? Is sample space, and in probability people like to use sample space versus population, and it's the set of all sample points or simple events. So you can see those repeated terminology: sample points, simple events, elementary events. They all mean the same thing. Of an experiment is called the sample space, or all possible outcomes. So notationally, we're going to use capital S for a sample space, E 1, 2, 3, 4 elementary events or sample points, and other letters A, B, C, D, and so on for any random events. We also like to use Venn diagrams to represent events. So events, in this case, if you're familiar with sets and subsets, events are sets or are subsets. And you can see here in this Venn diagram, this is event A, this is event B, and that's the intersection of A and B. I'll talk about those in a little while. So here we have 3 events, A, B, and C, and this is the intersection of A and B, that's the intersection of B and C, and this is the intersection of A and C, and that's here the intersection of all three of them. So that notation here is an intersection notation. Okay? So if you have a sample space with 6 elementary events, E1, E2 up to 6, or for ease, we're going to remove the ease and say these are just 1, 2, 3, 4, 5, 6, count them. Then we can think of as a representation of possible outcomes of a throw of a die. And that's a good way to think about it. Really, between dice and coins, we can model almost any natural phenomenon. Now let's talk about more. So if events are subsets, then we should be able to do union, intersection, and complementation as we do in sets. And so the union, so if I have a sample space S, my sample space would be the large set, the universal set here. And if I have two events A and B, the union of A and B would be anything in A or B. So the union notation is this notation here, or this, A or B for union. So the union is everything in A or B or both. So that's the whole thing. The intersection of A and B is anything that's in A and B. And for notation, the notation is people write A, B, or A without anything B, or A and B, or sometimes use the ampersand for notation. The complement of an event, we use A little c for complement. Sometimes people use bar for complement, or not A. Anything that's not in A would be the complement. And that's if that's your universal set, anything that's not in A would be the A complement. Another concept we talk about mutually exclusive events or disjoint events. So if you have two events A and B, they are said to be mutually exclusive if their intersection is empty. They have nothing in common. And you can see here A and B, there's an intersection here, so these are not mutually exclusive. If they were disjoint, nothing like A here and B somewhere here, then we would say they are mutually exclusive. Here's an example. So here's again a simple event where I have 6 points in my sample space. So this can be thought of a throw of a die. The die doesn't have to be fair. All sides are equally likely. So if I look at the event A, and you can see how events are represented, capital letters equally, you have the braces here, and you list the elementary events inside. E1, E3, E5, so this is the odds. B is the event 1, 2, and 3. The first 3 you observe either 1 or 2 or 3. So what would be the union of these events? So anything in A or B or both, so 1, 2, 3, and 5 would be the union. All the elements in here. The intersection is anything that's going to be both in both A and B. So 1 is in both, 2 is not in both, 3 is in both, 5 is not in both. So that's the intersection is only 1 and 3. A complement would be anything that's not in A but in S. So A1 is in A, A2 is not, A3 is in A, A4 is not, A5 is in A, A6 is not. So that's my A complement. My B complement would be, B is 1, 2, 3, so B complements would be 4, 5, and 6. Okay? Now question, are A and B mutually exclusive? Well, I look at the intersection and it has 2 elements in it. So they are not. So if there's nothing, and that's no notation for nothing, it's a phi. So that means there's nothing in there. You don't say 0. 0 is an element in there, but that's phi means empty. Now give 2 events in S that are mutually exclusive. So let me give you one, the odds and the evens. So if I take another event C, which is all the events, and A, there would be nothing in common, and these would be mutually exclusive events. All right, let's move on. Now, what's the probability of an event? This is how we measure the probability of an event, and we're going to talk about a couple of definitions. One is called the relative frequency definition. And if an experiment, if you take your random experiment, remember we started with a random experiment, and repeat that a large number of times, call it n, and we are interested in event A, so observe that NA times, that's the number of times you observe A. So now I'm throwing a die, and I'm interested in 6, say. I throw the die 100 times. I observe 6, say, NA 15 times. Then the probability of A would be, that's the probability of A would approximately be NA over N. Where N is the number of trials of the experiment, how many times you repeat the experiment, NA, the frequency of event A, how many times A occurred. And we know from chapter on data analysis that NA over N is the relative frequency of A. So the probability is nothing but a relative frequency with one condition, that N has to be large. So for the probability to be accurate. Oops, there's a... So if this one here, P of A would be the limit. There's the missing here, the limit as n goes to infinity of NA over N. So if you take, if n is infinite, it would be exactly equal. The conceptual definition of probability. So this definition defines probability as a relative frequency, and that was fine, but people couldn't utilize that definition much because they wanted to solve large problems, complex problems where a lot of math is involved, and this wasn't easily manipulative. So here is the definition that really became popular, which is due to Kolmogorov. It was in about 1932-33 when he came up with this definition. So if you consider a random experiment whose sample space is S, with sample points E1, E2, etc. We have all these points in S. Now for each event, E sub I, each one of them, of the sample space, we're going to define a number called P of E. So for each elementary events, we have a number called P of E that satisfies three conditions. We want P of E to be between 0 and 1. We want P of S, the whole sample space, to be 1. And we want, if we add all the probabilities of those events for all points in the sample space, they should add up to 1. So now we call this P of E the probability of event E, EI. And so that means, so if you look at the probability of event, what properties they should have? Probabilities can never be less than 0 or greater than 1. If I say, this means that if I throw a die and I ask the question, what's the probability I observe either a 1, 2, 3, 4, 5, or 6? It's 1. That's what P of S is. And if I want the probability of odds, I just add probability of 1, probability of 3, probability of 5. And if I want the probability, I can add those if I want if I add the probabilities of observing 1 or 2 or 3 or 4 or 5 or 6, they should give me 1. So what this does is we assign probabilities to events, while this one we compute the probability as a relative frequency. We'll talk about this a little bit later. Let's go do an example first. So here is, so now we define the probability of an event A is equal to the sum of the probabilities of all the points in A. So because in this definition we evaluated the probabilities of elementary events. So if we want a compound event, we add the probabilities that make up that compound event. Okay. So here I have a die, a special die with 10 sides, and it's not, each side has a different probability of falling. So from 1 to 6, each one has a chance of 1/20 of falling, and from 7, 8, and 9 sides have 1/5, and 10, the last side has 1/10 or 2/20 here. In tabular form, so we can list all these events 1, 2, 3, 4, 5 up to 10, and these are their probabilities. Okay. Question: calculate the probability of A where A is E of I greater or equal to 6. So then the question now, how do we compute that? Based on this definition, we want to find out what elementary events are in A and add their probabilities. So I should be more than 6, including 6. So what the elementary events in A are this: E6, E7, E8, E9, E10. And so to get P of A, we just add their probabilities. That's what we have here. P of A, P of E6, E7, E8, E9, E10. We add their probabilities from here that we were given, and we get 0.75. So that gives us a plan to compute probabilities of any events. First, you define the experiment, then you list all simple events as we did up, assign probabilities to simple events, because the assignment has to make sense, either as a relative frequency or because it makes sense. Like if you have a fair coin, probability of head would be half, probability of tail would be half. Determine the simple events that constitute the event, and then add up the simple events probabilities to obtain the probability of the event. And calculate the probability of observing, look at this example. Let's calculate the probability of observing one head in a toss of 2 fair coins. So if my random experiment is to toss 2 fair coins, my sample space would be head, 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 tail, tail, head, and tail, tail. And because the coin is fair, each one of these elementary events would have a probability of 1/4. Now I want the probability of observing one head. So my event A should have one head in it. There's 2 heads here, that's not in A. 1 head here, that's in A. 1 head here, that's in A. That's not in A. So A has 2 elementary events. P of A then equal 1/4 plus 1/4, which is half. Right? Interpretations of probability. Let's go quickly over this. In real application, we observe relative frequencies. We measure them as in data analysis. We don't measure probabilities, but we can estimate probabilities. So this is useful to know. But usually we get estimates of probabilities. At the conceptual level, we assign probabilities to event, with one condition, that the assignment should make sense. So if I toss a fair coin, the probability of heads I would assume would be half, and the probability of tail half. If I throw a fair die, I would assume probability of each side would be 1/6, because it makes sense to do so. And I can, if I take a die and throw it 6,000 times, I'll probably get each side close to 1,000 times. So experimentally I can verify that. In some cases we cannot verify our probabilities experimentally. We call them subjective probabilities. Say, probably some people doubt that Shakespeare wrote Hamlet. So if I tell you the probability or the chance that Shakespeare did not write Hamlet is 40%, 0.4. So what does that mean? So that's called subjective probability. But based on the definition, the relative frequency definition, that wouldn't make sense because I cannot repeat that experiment. But based on the conceptual definition, that makes sense as long as the probability of its complement would be 1 minus that, and all the probabilities would add up to 1. So it satisfies those conditions or axioms, and that would be fine. So that definition expands the notion of probability and makes it possible to use all the math, the calculus, and so on. Which we are not interested in that part anyway. So typically we would like to assign probabilities to simple events directly. Remember, to simple events, then use laws of probabilities to calculate the probabilities of compound events. So that's where we are interested in, compound events. One more piece, if you noticed up in this example, let me go up here. This experiment had 10 elementary events in it, and they all have different probabilities. So when I calculate the probability of A, I had to add the probability of these simple events. Well, if these were all equally likely, each one of them was 1 over 10, 1 over 10, 1 over 10, and so on, then I know I have 1, 2, 3, 4, 5 in mind, and all I have to do is just divide 5 by 10. That's when my events are called equally likely. So that's what equally likely means. So the equally likely probability defined on finite space, E1 up to capital N here, each one would have probability 1 over n. Now if I have any event A I'm interested in, it's going to be just count how many points in A, how many points in S, and A over n, or number of points in event A over the number of points in event S, and that would give me my probability. So that really simplifies things, especially if n is very large. So if I have an event which has 500 simple events, and I want the probability of a compound events that is made up of 70, then adding 70 numbers would be complex, more involved than just simply dividing 2 numbers. Okay. So here's an exercise for you to follow. Let me go over that. Toss a fair coin 3 times. How would we represent the sample space of that? So I have a hint for you here. I gave you 2 of them, and I want you to complete that. So that would be H, 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 and there's T, 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 and then everything in between. So H, T, H, 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 T, and so on. And there should be 8 of them, right? So you should get 8 of these here. And once you get those 8, you can tell which ones of them have exactly 2 heads, and then compute the probability of that event, and which ones has at most 1 head, either 1 head or no heads, and compute the probability of that event as well. So I'll stop here, and next lecture will be on the laws of probability. Thank you.